All right, should we, oh, that's echoey. All right, should we get going? So thanks for coming, everyone. I'm Greg. I am co-founder and CTO at Undo. I'm going to be talking today with Dewang, who's solutions architect with Synopsys, working on Coverity. We're going to talk about some of the under the covers on advanced Linux C++ debugging tools. So I'm going to go first, talk about some of the stuff that I know about, and then Dewang is going to talk about what he knows about. Maybe if I come away from that to go less echoey. Is it just me? Is that a terrible echo? Can everyone else hear the echo, or is it just me? Yeah. Are both mics on, maybe? Is there anything we can do about that? It's just the room. All right, just the way it is. Okay. I'll try and get past it. Okay. So I think debugging is our dirty secret as programmers, right? Most programmers spend most of their time finding and fixing bugs. And if you dispute that, just think like, how often does it work first time? Right? I'd like to fancy myself as better than average programmer. And what's the longest program I can write and it be correct straight off the bat? 10 lines? 30 maybe if I'm really careful and pushing it. And that's if it's a new program. If I'm changing an existing program, an existing complex piece of code, then that number is, I think, depressingly close to 0 lines of code that will be written without a bug, right? And it's really the process is just trying to understand what happened, right? My program did something different from what I was expecting it to do. Now, if you're a C++ programmer, as I guess most of us here are, then you've chosen the language that's like very close to the metal, right? You must have a reason for choosing C++ over something higher level. Hopefully, that's a better reason than it makes you feel clever. Usually, it's like performance or something, but you're deliberately close to the metal, and you kind of need to know what's going on. And when you're debugging these systems, you need to know what's going on. And you need to use the tools that are available, right? And I think that's really, you can't be a really good programmer if you're not very good at debugging, and that means you have to use the tools that are available. But you kind of really need to know what the tools are doing as well. Because when life gets really fun, when you get that kind of sort of delicious mystery of like, the thing I'm observing can't possibly happen. Everything is just, I cannot have a model for what the hell is going on here. And then if the tools actually, if you misinterpret what the tools are doing, then that can even lead you astray and make it even worse, right? So I think having a basic understanding of how these things work underneath is essential. So I'd like to divide these tools up into these different kind of categories, right? The debugger, what we all think of, and I'm going to spend most of my time talking about that today. Not how to use it. I've done other talks on how to do lots of cool stuff in GDB, but how it works underneath. There's record and replay tools, which is obviously something that's close to my heart, where I'm from. The dynamic checkers and static analysis, which Dewang will talk about. So the debugger is really, it's saying, what is my program doing, right? It's the ability to kind of freeze time. It's a bit like, there was that style in movies that was very popular, sort of popularized, I think, by The Matrix, and then where they sort of freeze time and the camera kind of pans around and you can see everything kind of frozen. And then that style got copied by like everybody for a few years, including every commercial and everything. Well, that's kind of what I think of the debugger like. And you can see everything, and then time can just run again, right? And then you can stop again and have a look around. So it's very powerful at telling you what's my program doing right now. Whereas the record and replay tools, they really tell you, what did my program do? What happened? Now, there's a bit of overlap here, admittedly. Debuggers can give you a backtrace, which is kind of the best they can do about telling you how you got here, and obviously that's very limited, but can be very useful. Whereas if you've got we stick with my analogy of Matrix film direction, like you've got that ability with the replay systems, you've got that ability to go and see everything from any angle you want, and like a Time Lord, you can sort of move time back and forth to wherever you want to be and see everything for any point in time. The checkers, really, they're about, did a class of a certain thing happen? Buffer overrun being the kind of canonical example, but there are all kinds of others to do with race conditions or out-of-order lock acquisition or something like that. So you're looking for instances of, did this specific thing happen when I ran my program? And the static checkers are saying, could this thing happen? They don't even have to run the program. Okay, so here's the so the big difference, of course, with the dynamic checkers. You have to. It won't tell you whether a buffer overflow might happen. You have to cause the buffer overflow in your testing or whatever in order to detect it. It can tell you where it happened, which of course is extremely useful. So let's get on with GDB. I'm going to talk everything about GDB, but any Linux debugger will be working in basically the same way for the purposes of this talk. So this is LLDB or TotalView or whatever your debugger running on Linux, or indeed any Unix-like system is going to do basically the same thing. So you've got GDB, which is a process, right? Just a regular user-level process. Doesn't have any special rights or anything, and that's talking to your program here. We're going to call it Hello World, but whatever your program is. And it's over this kernel API called ptrace, right? Which is a really lousy interface. It's a horribly designed interface, but it's pretty powerful, and that's what it is, so that's what we have to use. And then information goes back, or asynchronous notifications go back from the program to the debugger over signals. So let's just take a step back to how signals work. So on a Unix system, when a process receives a signal, a lot of the time it's going to terminate. That's often the default, most often the default behavior. Depending on what the signal was and how the system is configured, maybe it dumps core. If it's SIGINT, it won't. If it's SegV, it might. But maybe the program's been configured to ignore the signal, or maybe the default behavior of the signal is to be ignored. So signals like sig alarm, its default behavior is ignore. Or maybe the default behavior is to stop the program. So signals like sig TT out, sig TT in, or sig T stop, or sig stop. Their default behavior is to stop the program. And if the program is so set things up, it can run a signal handler on receipt of the signal. And the other thing you might get is if your program is being ptraced, right? So if it has a tracer, then on receipt of a signal, it goes into a tracing stop, which looks very like a regular stop. You can see this if you look in proc PID status. You see the status of the process, and if it's T, that's a tracing stop. It means it's got a tracer and it's received a signal. So in this world, so Hello World here it's received some kind of signal. Let's say it's sig alarm, whatever it is, doesn't matter, and it's now gone into this stopped state. So that's why I've shown it red. It's stopped, and then the debugger will continue it with ptrace_cont, which then will unstop the target process and run it forward. Right? GDB calls the process being debugged the inferior, which I always think is a lousy name, but that's what it calls it, but we can call it the target or the debuggy or however you want to think of it. So it calls ptrace_cont, and that process now starts running until something happens, until actually it receives a signal. And when it receives a signal, it will go stop into that tracing stop, and the debugger gets notified. And actually, in my little diagram, I could have made GDB go red while the debuggy was running, because while the inferior was running, because that's typically what happens, but it doesn't have to. And actually, you can run GDB in non-stop mode. There's nothing about ptrace that requires it to stop. Typically, though, what it'll do is a wait PID call and stop waiting for that notification from the signal to come back. So signals only reach the tracee if they're passed in via this ptrace_cont call. So I said it was a lousy interface, and you can see proof of it here. So you've got this ptrace_cont. The first argument of ptrace is an opcode. I think, by the way, if ever you find yourself writing a function whose first argument is some kind of opcode, then please don't. It should be several functions in my view, but whatever, that's what ptrace looks like. And you can see, obviously, it's completely not type safe when you pass in these void stars, but the last argument there is sig alarm in this example. So that will actually deliver the sig alarm to the tracee. And if there's a signal handler for that, it will run, or if it's something like a segv and there isn't a signal handler, it will terminate the process. But the tracee will only ever actually see the signal if it's passed in via ptrace_cont or one of its friends, ptrace_single_step or ptrace_syscall. And if the signal handler is blocked, then it will just mark the signal as pending. The handler won't run in that case. And similarly, if it's set to ignore, it'll just be ignored. So breakpoints, when your target process hits a breakpoint, that's just a signal. That's a sig trap, right? Now, if it's a breakpoint on x86, what the debugger will have done is poked into the text section a special instruction, which on Intel is int3, I think we'll come to that in a bit, which generates a sig trap, and then the debugger is notified in just the kind of the normal way. Likewise, Control-C, right? So if you run your program within GDB and it's busy and you hit Control-C, there's no special, like GDB's not, well, at least if it's not doing remote debugging, GDB's not special like in this way. It doesn't do anything particularly special. It's just that the program you're debugging, it has a terminal, probably. And when you hit Control-C, the TTY for the controlling process group will send SIGINT to all of those processes. So the process that's being debugged gets stopped with a SIGINT, and then GDB gets notified of that effect, and then it drops down to the prompt, and you can do what you will. And so you can see this. So if I go info signals. So here's the default behavior for all of the signals in GDB. So you've got these different things you can say, whether it's going to stop, or whether, and if you say no to stop, then when GDB sees a signal, it will just feed it straight back in to the process. Whether it's going to tell you the user that it's happened, or whether it's going to pass it in. So it doesn't have to, right? So that's the thing. When the tracee gets the signal, the debugger, it's up to the tracer whether it's going to feed that signal back in. Usually it does, but in things like Control-C, which you can see here, it won't feed it back in, because most of the time that would just cause the program you're debugging to terminate, right? So this is my attempt at the Unix signal algorithm. I think this is roughly right. I'm almost certain there'll be some kind of exceptions to it. But so sigkill and sigstop are special. You cannot set a signal handler for either of them. You cannot block them. You cannot ignore them. So if a process gets a sigkill, even if it's being traced, right? Even if it's being p-traced, even if it's being debugged, when it gets a sigkill, that's it. Game over. The program is terminated. It becomes a zombie until that result is reaped. Otherwise, if it's a sigstop, the process will go into a stop state. Again, you can't have a signal handler for sigstop. You can't mask it. You can't ignore it. Otherwise, if the process is being traced, it goes into this tracing stop. Actually, this is not quite right. If it's a sigstop and it's being traced, it still goes into a tracing stop. So that's a useful signal that debuggers will often use when they want to stop the target process, because you can know, as a debugger writer, you can know that it doesn't matter what the target's done in terms of masking the signals or setting signal handlers or ignoring signals. It can't mask sigstop, it can't ignore it, so they're going to do what you want. Likewise, then you go if it's blocked or ignored or as a handler, otherwise, last thing we do is terminate the process. So ptrace has a whole bunch of operations. So ptrace-cont we've already seen. Single step runs it forward one instruction. You can run forward to a syscall get and set registers, and peek and poke memory and all that stuff. There's in fact a whole bunch. I'm not going to get into all the details on what it does, but it's quite rich. If you run with ptrace syscall, that's kind of like ptrace-cont, but it stops when the process issues a system call. Actually, it stops twice, once on the way into the system call and once on the way out. And on x86, there's a nasty hack where you can inspect the AX register. If it's -38, that means it stopped on the way in. -38 is enosys, so there's no way that a system call can actually return enosys. So that's why they picked that magic value. I believe on other architectures, there's no way to tell whether it's on the way in or the way out. As a tracer, you just need to count. Here's a certain thing that so I'd been writing to the ptrace interface for, I'm a bit embarrassed to say this, but for multiple years before I figured out that what happens with syscall restart. Because the kernel does a really good job at kind of hiding this and making it all transparent nearly all the time. So when the process gets stopped, it goes into one of these tracing stop states that I spoke about. Let's say it's deep in a read system call or something. It's blocked reading data from the network, and you do Control-C, and it goes into a tracing stop. Actually, it doesn't stop deep inside the kernel. It percolates all the way back out. The system call returns to user space, and it's at the time the system call returns to user space, then it becomes stopped. And if you think back to the earlier versions of Linux that had the big kernel lock, this was kind of needed, right? Because otherwise, well, you wouldn't be able to do anything if it was stuck in the kernel holding the lock, and that's still the way that it works today. It returns back to user space, but before executing any code in user space, then it's in that stopped state. And it has a special magic return code, something like e-restart sys. There's, I think, -512 through to -516 of these e-restart sys and friends. And this is a special return code that tells the kernel when it next gets a ptrace cont, when it's going to be continued, it's going to magically re-enter the system call and restart it. And most of the time, it will do the right thing with timeouts and things, so it doesn't reset the timeout to what it was. So you should never see a system call return e-restart sys as in user space code. Should never see, but there are bugs, especially in certain versions of kernels. One that can be, I think, most problematic is the Rel 6 kernels and CentOS 6 and the like, where there was actually, I said ptrace is this lousy interface. There was an attempt to make it better with a thing called utrace, which then was going to be a new interface, and then ptrace would be a kind of personality onto that. And Red Hat adopted it and put it all into Rel 6 kernels, but it never made it, and that's kind of died, that attempt. And that implementation was a bit iffy. So if you're debugging a process, you might see a function, you might see a system, particularly on Rel 6, you might see a system call return e-restart sys. That's not what really happens. That's an artifact of the fact that you're ptracing it and in your debugger. I mentioned this earlier, just touched on this earlier. So breakpoints on x86 at least is this int3 instruction. It's a magic single byte instruction. So int is to raise an interrupt. And usually on x86, int raise an interrupt is 2 bytes long, the interrupt opcode and the 0 to 255 interrupt number that you're raising. But a 2-byte breakpoint instruction would be problematic if you have a single byte instruction on which you're trying to place a breakpoint, right? Otherwise your program could end up branching into the middle of that instruction. So there's a magic bytecode OXCC. The debugger puts that in. You should never see it, right? Because the debugger will, when you look at the memory, the debugger will take that out. But if your program, for whatever reason, is reading its own code, you might observe it when those breakpoints are set. When an int3 instruction is executed, the kernel stops the process with a sig trap, and you get all the usual thing you see. There's also hardware watch points, which obviously are very, very useful, right? So that you can watch data and trigger a trap when that data is changed. Those are set by the debug registers on x86. I'm setting everything in x86 terms, but most architectures have some equivalent of this. DB0 to 7, actually 4 of them are for addresses, the other are control registers, so you can set up to 4 at a time. You can set them to trap on memory reads or writes, or executes actually, so you can implement breakpoints using the debug registers if you really don't want to write to the code, but there aren't very many of them available. And you don't write to them directly from the program, so it's configurable on x86, but I think Linux means you'll get a fault if you try to access the debug registers directly from your program, but the debugger will do it via ptrace poke user command. Okay, so then we've got this. Let's get on to a bit more, that's how kind of the ptrace interface. Let's get on to dwarf info now and how our debug information is represented. And I suspect we've all kind of fallen foul of this at some point. So debugging with attributed record formats, that's a kind of strange acronym, and I was unsurprised when I looked it up earlier to learn that it is in fact a backronym, and it's called dwarf because it was made at the same time as the ELF format was made, and they decided that would be kind of cool. So it doesn't really, it's not really what it stands for. But anyway, it contains the debug info. It contains a description of your program that the debugger can read to give you that kind of symbolic information. So at the simplest level, it will map a program counter to a source line. So when your program is stopped at program counter, OX1234, the debugger can look in the dwarf information and see, oh yeah, that corresponds to foo.c line 42. But contains all sorts of information as well, and all the type information, classes, templates, all kinds of things that the debugger might want to know. You can hear some useful options. So -G is the default one. That's the easiest one to get debug info. But actually, that defaults to -G2. So -G is like -O. You give it a number afterwards to specify different levels. And the default -G is level 2. You can go -G3 to get everything, which generally I recommend. That's generally useful, -G3. It's independent, completely orthogonal to the optimization level. But obviously, the more aggressively the compiler has optimized your code, the more quirky your experience might be when you come to debug it. It's not laid out linearly, and so you can think you're going forwards, but you jump back. But -OG is a useful optimization level, so sensible optimizations, but nothing too crazy, so you get a sensible debug experience. But often you're trying to debug, you're trying to debug production code, and you want to do that with full optimizations, and you can, and it does. The experience is obviously your experience will vary, but we'll talk a bit about that right now. So one of the most annoying things when you're debugging optimized code. Oh, by the way, if you do -G3, one of the nice things it will do is all the inlined functions, it will kind of make that all go away. So as you're stepping through, it will mostly look like inlined functions and not inlined, which is very helpful. But yeah, you try and print a variable and you get variable optimized out, right? So we've all seen that, I expect. So let's have a look at what this means. So here's a little program that I'm going to compile with optimizations. And when we load it up, and so here I am at the beginning of my program, line 7, and if I print foo, it says variable optimized out. I think this is a really unhelpful error message because it kind of implies, to me at least, that just doesn't exist anymore. The compiler's been able to get rid of foo completely. It's not what it means here. What it means here is it's not live, but it hasn't actually been optimized away. If I do a next and then print foo, hey, voila, there it is. Right? So let's look at how that all works and what GDB is doing. So if I look at readelf minus debug dump. So this shows us the dwarf information, right? So dwarf is this file format. It's fairly simple, really, and it's just this tree of objects, and there are tags, which are kind of the nodes of the tree, and the tree structure, as you might imagine from your program layout, and nested blocks of code and types, structures with structures and classes and templates and all that, all put together in this tree, a little bit like an AST, but not quite. And here's everything. Of course, this has got everything that I've included, all the type definitions and everything, so GCC can describe that. If you remember, my variable was called foo, so let's have a look at that. So here's foo, and it tells me where it is, so it's in file number 1, which will be indexed elsewhere to optimized.c, the file name and the line number and everything, and the type, of course, and it has a locations list, and this defines where foo is live. And I can actually look at that, slightly simpler view. I can go debug dump equals lock and get just the locations list. Now, this program is very small, so this is obviously quite small. So here's the locations list starting at A. It's actually a list, it's a full list. And these are the ranges where foo is available, right? So if I go back, let's look at the function. So I can see from the disassembly, it's never actually writing that foo value to memory. It doesn't need to. Rand returns it. It's in register AX, and it just keeps it in a register. But the dwarf info, that's fine. It can tell us that, right? It can tell us that at these lines, it seems to have a 0 size range here, so I'm not sure what that's all about. But from here, from offset 1074 to 1078, if I look here, so I can see here it is. Here's the 074 to 078, and it tells the debugger that the values there in register RAX. And actually it pops around different registers here. And it's actually telling us, I think, well, I haven't actually confirmed this, but I think what this means is that the value foo is what's in RAX plus 1, right? Because my code, if you remember, did foo plus plus. And then at the end, it's just in RAX because that's the value that gets returned. So modern versions of the compiler and modern versions of GDB, or whatever debugger you're using, are able to do an okay job, at least, pretty good job, of tracking values through register states just as long as they're live. Now, of course, if you're using reversible debugging, it's even better because you can go back to when it was live, when it's kind of become unlive. But even if you're using a regular debugger, often you can just step forwards a bit and find out what those values are. There's a nice little tour of dwarf and all that good stuff. So you can tell, these are all GCC options, by the way, so you can tell GCC quite a bunch of things, but actually, if you just put -G3, it kind of does everything. Even macros, actually, which is quite cool. Let me just quickly show that. So if I go just -G on here, and I load that up, and I start, and I print val, it goes, I don't know what val is, right? Because it says preprocessor macro. It hasn't gone through the compiler. But if I go -G3 and repeat, ta-da, it knows about macros. So particularly useful when you've got macros that sort of expand. You can can convert data structures to extract the bit fields out of data structures or whatever. When that's done by macros, which sometimes it is, that's quite useful. Obviously, you shouldn't be using macros, but maybe you're trying to debug someone else's code. Now, related to dwarf format is stack information, CFA and CFI, which is call frame, address, and information, respectively. So depending on how you compile things, you may or may not have frame pointers. And in the modern world, more than likely you don't. Any optimization on 64-bit Intel, the compiler will take away frame pointers so it can use the RBP register as a useful general purpose register. And this means walking the stack is slightly painful. But it's worth it for the extra register that you get. And so with the CFA and CFI, what you get is essentially a mapping of, for every program counter or range of program counters, what offset from the stack pointer is the beginning of my stack frame, right? And then that can be, so then you can use that to print your backtrace or see it, and that's on the CFA, and with CFI, you get more stuff like locals and everything else. And actually the exception unwinding mechanism and C++ will use some of this stuff. So it's kind of related, but different from dwarf. As this is a C++ conference, let's just do a little bit of C++. So catch points pretty cool in GDB. They let you stop. So breakpoints obviously stop, but at a given line. Catch points can let you stop when kind of interesting things happen. So here's my bit of C++ code, -G3. So let's. So I can go catch, throw, exception. Now we'll catch any time the exception is thrown. I can also catch, which is a bit mouthful, but catch is the catch. And if I look at what it's done, it's actually inserted just a couple of breakpoints, and it's given me handily the address here. So I can look at that. If I look at that address, info line, that we can see, sure enough, that's at the CXA throw label, and unsurprisingly, that's a catch, right? So these are routines within the C++ library, which the exception mechanism will jump into when it's throwing and catching exceptions, and then GDB will put breakpoints on there and then can filter on the exception type and all that good stuff. You can also catch syscall, which uses the ptrace syscall thing, right? So you can say catch all syscalls or catch a certain syscall and run forward until that syscall happens. Threads are kind of interesting in the debugger world. So the thread library, this is all kind of pointless these days because pretty much every threaded C++ program on Linux is going to be using just libpthread, and it's all kind of standard. But it's designed such that you can have different threading libraries, and in years gone by, that was actually more common that you would do that. So the threading library provides this libthreaddb, where db stands for debugger, and that provides different routines that the debugger can call to look up things like thread local storage. So when you try and print erno in just in a regular C program, that will actually go through libthreaddb if it's threaded program, because erno is thread local. And GDB does that kind of all automagically for you. Just a little plug. I'm putting together a series of small kind of bite-sized 5-10 minute tutorials on all kinds of things GDB. So it's kind of a lot of content from previous talks, but a lot of new stuff as well. So you might want to go and look at our wittingly named GDB Watchpoint series for more of that kind of stuff. Enough of GDB and the debugger. Let's talk about dynamic checkers. And we're talking about address sanitizer and Valgrind here. There are, of course, many others. They're all both address sanitizer and Valgrind work on this. They have this notion of shadow memory, right? So back up a bit. What we're trying to do here is detect invalid memory accesses at a much finer grain than the hardware will allow, right? So obviously with modern systems, you've got pages, typically 4K, might be much bigger than that, and that's your kind of the granularity with which you can mark memory as accessible or not. And what we're trying to do with both Valgrind and address sanitizer is do that at a much finer grained, per sort of object level, much finer grain than the hardware will support. So what they do is create these shadow maps. So the memory, every chunk of memory, does this work? No, not really. Every chunk of memory will map down to the shadow. The shadow is a smaller bit because it only needs a few bits of information for every, say, 8-byte word. So the shadow is smaller than the memory it shadows typically. And it just has sort of information about whether this, so that way, both address sanitizer and Valgrind can look up, is this address valid or not? Now, Valgrind works with binary JIT translation, right? So you can just take your program compiled, however it's compiled. Maybe you don't even have the source code to it, and you can run it through Valgrind, and it does it through JIT translation. The sanitizers work by changing the compiler. These have different trade-offs, of course. It's nice that you don't have to change the application, change the way you compile. With Valgrind, it does mean it is quite slow, and there are certain things you can't do. So address sanitizer, because the compiler is generating the checks around each memory access, it can do more stuff, right? So one of the things it can do that Valgrind isn't able to do is detect buffer overruns on the stack. And the runtime overhead is much less. So they report typically around sort of 50% to 100% slowdown. So it's still, very real and measurable, but it's much less than you'd get with something like Valgrind. But what both techniques are doing is every chunk of memory has these red zones at the beginning and the end, right? And so if you do a malloc of a certain size, anyway, if you do a malloc of, say, 32 bytes, actually the system's going to allocate more than 32 bytes because it's got some bookkeeping information that needs to go with that mallocked chunk. But if you do it with Valgrind or with address sanitizer, they have their own mallocs, they intercept malloc, and they make it even bigger, and they put these red zones at the beginning and the end, and then through the shadow maps, these red zones are marked bad, right? So if your program touches these, it knows it's a problem. One thing to be aware of course, is the smaller the red zone, then if you stretch over the buffer with a certain stride, you can go right over the red zone, and it won't notice. So bigger red zones will catch more types of errors, but of course consume more memory. So that's it for the sanitizers. Let's get in now to record and replay systems, and something sort of close to my heart. So, as I say, it's this sort of control of time. It's being able to see exactly what happens. I think we have time where I can just show a very quick demo of this, if you will indulge me. Is that readable? Just about. Is that, well, maybe not at the back. Let me, I think there's a, see if I can figure this out. But I haven't got any, oh, that's not doing what I wanted it to do. All right. No, that's not done what I wanted. Never mind, let's go into normal mode. So here I've got a little program, and I'm going to run the program inside the debugger. Let's go onto the VPN so I can get a license. Okay, let's get rid of that. It's from the previous time I ran this little demo. So apologies if you've seen this demo before, but I just want to show what we mean by record and replay or reversible debugging. So I'm going to run my program, and it's crashed. and I come through assert 0. Right, well, let's have a look at what's gone on here. So I've called this function cache calculate, which given a number is supposed to return its square root, and I've given it 255 and it's returned 0. So clearly cache calculate has returned the wrong thing. I can see from my stack trace here, down here, I'm not actually in my code assert 0. The debugger's kindly put me there, but actually it's in this raise function here where the program has stopped. All so far so normal. So you can do that with a regular debugger, just looking at, as I said earlier, looking at the stack trace is kind of the closest that most debuggers give you to like, how did I get here? But I need to know what happened inside this function, right? Cache calculate returned the wrong thing, and I need to know why. So what I'm going to do is hit this button here, which is like an uncall, which is kind of popping up the call stack, but rather than guessing, it's really moving back. My program has definitely been here. All the globals and everything are go back to what they were. And now I can start to step back through time. And now if I go here, this is right after cache calculate returned. So I can go in to the function and I can see what it returned and why. So it's returned the ith entry from the cache. I here is 88. So this looks like typical programmer's worst nightmare. Sure enough, my cache contains bad data. My cache tells me that the square root of 255 is 0. So someone stomped on my cache. I've got no idea how or when that happened. Is it a logic error? Is it a memory error? I don't know. Well, what I'm going to do here is add a watch point. Normally you'd set a watch point. I'm going to make this watch point persist across stack frames. Normally you'd set a watch point and run forward until the data changes. I'm going to run backwards until that data changes. And that's going to take me back to the line of code that's where that happened, the smoking gun. So I've gone back in time. I've gone back in time to where the structure contains good data. Actually, I can now step forward. Watch the data here as I step forwards. We'll see, this is like watching live action replay if you're watching sports on TV or something. So as I step, that's it. That's the corruption happening right there. Let's just back up a bit and see if we can see what's going on. So writing square root adjacent and operand adjacent into my cache, and I can see here that operand adjacent is -1. So I've tried to take the square root of -1. You can't do that with integers, hence that's garbage. Well, what's going on there? Why has that happened? Well, let's just add another watch point to that and go back again. And okay, it's being set here. So operand adjacent is being set to operand -1. Operand is 0. So what the program tried to be smart, just tried to populate one entry either side in the cache. And that's called the, so when it called the function, it returned the right thing. It called the function with an argument of 0, and it returned 0, as it should have. But by being smart with this locality of reference, it's left one entry in the cache in a bad state, and I didn't notice for some time later. So that's kind of what you can do with these replay systems. So essentially what we're saying here is you can go back to any instruction that executed, and you can see any piece of state, right? Any value, any piece of memory, any register value for any instruction that executed, which clearly is just a huge amount of data for anything but the tiniest of programs, right? So clearly we can't store all of that. Even if we tried to store just the diff, just the delta between what's changed each instruction, that would still be way too much information, right? Billions of instructions operating every second, it's 8, 16, 32-byte record every nanosecond, roughly. That's just not going to be practical either. So what we do, and this is true for RR and for live recorder, what we do is to just capture the non-deterministic stimuli and exploit the natural determinism of computers. So when I'm stepping back in that demo, what's happening under the hood is it's going back to a snapshot and playing forwards to where it needs to be, right? And so we're recomputing previous states rather than trying to store everything. Now for that to work, then we need to capture those sources of non-determinism, right? Computers are completely deterministic except when they're not. And for a user mode application, you've got several sources of this non-determinism, namely system calls, thread switches, signals, asynchronous signals at least. Some instructions are non-deterministic, so read the timestamp counter as an example. Modern Intels also have a get me a random number instruction. And shared memory access is shared with the process or shared with the device or something. But we just need to capture those, which is typically a tiny, tiny subset of what the program is doing, and everything else can be recomputed. Now there's another problem though. We need to know where we are in time when we're replaying. So when when that demo steps forward a line, it has to stop at the right time. And if it's inside a loop, you can't use the program counter because loops, right? So we have to know how far through the program we are, not just so that we can step nicely with reverse step and things, but so that we can replay signals and other asynchronous non-deterministic events at exactly the right time, right? So the problem with this kind of technology is that if you get it even slightly wrong, everything unravels very quickly. It's sort of like it's very kind of, you've got to get everything. You've got to capture and replay perfectly every single bit at precisely the right time. So RR is built on performance counters, right? So modern CPUs, at least modern Intel CPUs, have sufficiently accurate performance counters to count the number of retired taken branches that it can give you an accurate time of how far you are through the program, and these can be exploited. So they're nice and fast. The program runs without instrumentation, nice and simple. You don't have to write too much code to take advantage of them. The only thing is they're not always available, so they don't work on AMD CPUs. They're not always available in the cloud. They don't work on ARM, but where they are available, they're very good. But they also can't capture everything. So things like shared memory accesses and asynchronous operations are problematic. And they use the thing called the precision event-based sampling PEBs in order to generate an interrupt. So I don't only need to know exactly where I am in the program. I need to be able to go back to a precise state in the program. And you can configure the Intel performance counters to generate an interrupt after a certain number of things have happened, right? And so that's how they do that. Whereas with Live Recorder, which is from Undo, we use a JIT and we binary translate the machine code as it's running, which does impose more overhead, but does have the advantage of not relying on these things that aren't always there, and can cover cases like shared memory and asynchronous stuff. But basically they're kind of the same, but they're just using different techniques to get the same information that we need. So that's it for my very quick run through of those various types of tools. I'd now like to hand over to Duang, who's going to talk about covariate static analysis.
All right, before I start, a real quick question for you guys. What do you think would be the coolest way to make money for C++ programmers? Inheritance, of course. It's free and efficient, right? Okay, well, this section I'm going to talk about static analysis. Like Greg said, I work for Synopsys, and I support the product Covariate. It's a static analyzer. So what do static analyzers do? Well, what they do is they take source code, okay? In case of languages like C, C++, they will compile them and then generate a semantic representation that includes an abstract syntax tree, various call graph elements, right? And then compute, different paths, and then go through those paths and find problems in your code, right? So all of this is computed, and this is done statically, and it's not during runtime, right? So when it finds problems, they will present, I know it's not readable, it's okay. Like in red, it's like annotation of steps, which leads to the ultimate problem in your code, yeah? And then these defects are very consumable in various formats. If you are running the static analyzer on command line, print on the command line. If you're using some IDE, the analyzer can often be driven inside your IDE, so your code will be overlaid with the problems they find. It's pretty trivial to push the results into code reviews, pull requests, right? And there are quite a few static analyzers in our industry. And so the way I kind of like to think about static analyzer is this way. I mean, what is the main motivation behind that static analyzer, and whether that analyzer ultimately is your friend or not, okay? So there's a group of them where their attempt is to find anything that can potentially go wrong with your code, okay? Where the false positive rate can be as high as 80 to 90%. So that class of static analyzer is typically used mostly for security researchers, okay? So they need to look at all possibilities, find the research, and then kind of find the needle in a haystack, right? So if you are using static analyzer today and you end up facing with too many false positives, just remember that's not your friend. Because if you are triaging everything that's in there, you're kind of doing the work of the security researcher, right? Then you don't have time to code, okay? And then I would say the other class is what's already built in with your compiler, with your tool chain. I say those are your friend, but I think they're typically focused on trying to get you something quick right there, right? And then I would say the last class of static analyzers, they tend to be much more conservative, right? They gotta have very strong evidence before they put it into a report that it's a defect, yeah? And I would say that class, make that your best friend. I'll quickly go through this. So I don't know if you read this paper. This is back in 2002, Linux kernel version 2.2, research work at Stanford, where they created, this was the original version of Coverity actually. They found 200 some, or several hundred very important defects in the Linux kernel. You know, this is like many, many years ago. So since then, we have come a really long way. The Linux kernel team still uses Coverity today pretty judiciously. Actually, I should ask, anybody here work on the kernel? Okay, we have a hand there. Oh, actually, we should give him a round of applause. Because that community, they're kind of my heroes, right? If you look at our planet, that's probably one of the most important code bases, you know, we have, yeah? But it's very public. If you go into Git log and then do a keyword search on Coverity, you'll see thousands of references of Coverity. They like Coverity. They give credit to Coverity when they're fixing stuff based on what Coverity has found for them. So you'll see this table right here. On the left column is a list of checkers. So these are top checkers in terms of total number of issues that team has fixed. And I pulled this data back earlier this year, March 2019. So you'll see like the third one, dead code. That usually means like you have a if some logical expression and then there's a blocker code, right? But if that logical expression can never ever return true, then that blocker code becomes dead code, right? So that means the developer has made a mistake in their thinking, yeah? So you can see that for dead code, the kernel team has fixed 968 to date, right? 64 dismissed, right? So 486 outstanding. So outstanding usually, based on what I know, is usually in areas where they don't care that much, right? But the thing that I want to highlight for you guys is the dismiss rate itself. It's really low, okay? Yeah, so if you guys are using a static analyzer, have this kind of rate, remember, then that's your friend, okay? So now I want to get under the hood a little bit about static analysis. So on the left-hand side is an example code where it's being annotated with the problem. And on the right-hand side is actually an example checker. It's a domain, you know, it's a functional language. Coverity has actually recently started opening up the analysis engine, the AST, the code graph to developers. So then you can create your own custom analysis, if you will. Okay, so I'll walk you guys through. So on the left, right, this is a very simple problem. We have malloc here, right? We have a, if it's odd or even number here, just kind of random. If it's odd, then we will free the allocated memory, right? Otherwise, when it goes out of scope, you know, then you have a leak. Okay, so let's have a look at to see how the checker looks like. So the way to think about this is to say, okay, I'm going to define a pattern where it is a step in the call graph. Okay, and then where it's a function call, the function identifier is malloc. Okay, and then similarly, we're going to look for a step in the call graph where it's a call to free, where the function identifier is free. Okay, ignore the rest. It's, okay, and then, now if you think about this, we really need to match the allocation versus the free, right? You cannot just take random allocation and random free and where they don't line up, right? They don't reference the same object of memory, right? So the trick is to line up the paths where the object you care about is lined up. Yeah. So there's a feature in our code.xml where we could say the called expression E, whatever the pointer is, becomes the key. Okay. And then here's a checker itself now. So I can give the name to the checker, right? And then so then what the checker does is to say, okay, for all functions in global set, so just all functions, where all paths involving the function where it matches the sequence, right? You have at one point alloc, and then this arrow-looking thing. This can be chained together. So if you have multiple call sequences you care about, and then where there is no call to free, right? Easy enough, right? Okay. Yeah. Okay. So before I get to the demo, I just want to give you a flavor for like, why or when you might use something like this, right? So I was working with a customer, really big cloud company. They have a security policy to say anything that goes into storage must be encrypted, right? So you can imagine how to implement a checker similar to this, right? Then is to start with function patterns where, 5 more minutes, okay. So the use case would be very simple, where if you track all the operations where you can cause a write to storage, right? And then you look up in the call graph that's where this function exists, and then if there's an encryption operation, right? And then furthermore, you want to make sure that the encryption happens to the same object. Now you lined up. So every pass that comes through that does not have the encryption done, then that's a problem, right? So like if you are doing code reviews, right, you're frequently catching people, or you see review comments like, don't do this or don't do that, don't do this in this context or whatnot. That's a good time to use something like this, okay? So really quick on demo so you can see how this looks. So this is command line. So Coverity has a build wrapper called code build, where we say, this is where we want to put the capture code, and then you can put the compile command like this.
Nothing on the screen.
Oh. Okay, great. All right. So I would hit a command like this. So the build wrapper will monitor the compile. So anything that gets compiled, it will pick up. And Coverity understands all the compile flags, and then so it knows how to compile and generate the semantic representation that's exactly equal to your code. So like this CL, this is oh, okay, sorry, yes. Okay, is this better? Apologize. Okay, is that better? Okay, so you could replace the CL here with CMake, Maven, or whatever build you have. So everything that's gets touched will automatically pick it up. So so in this case, I only have one compile. So you can see it there. So then we can do conf analyze, just like that. So here it will compute the call graphs and AST and all that, and then run the analysis. So this resource leak is a default checker that comes with Coverity. So already found that. So the question is, how do we trigger that custom checker I showed you earlier? So we do this. So I'm going to disable all the default checkers that comes with Coverity, and I'm gonna just enable that particular custom checker I showed you earlier. Okay, and then if I want to look at the issue locally, and you'll see that the checker name here, right, came from the custom checker. So yeah, and notice, right, you get several things automatically. You'll notice that in this particular branch, where if it's taking the false branch, that's when you go out of scope, you're gonna have the leak, right? You notice I didn't do anything that had to do with this conditional branch right here, right? That's because Coverity in the background, when it computes all these paths, that path already pre-computed. So when I express that this is a particular sequence I care about, I don't need to worry about these different paths, right? So it knows how to evaluate this I mod 2 equals 1, for example. Yeah? Okay. Yep. So that's static analysis.
Yeah, thanks to Ang, thanks everyone. I don't know if we have time for maybe one or two really quick questions. I'm seeing a sign session is over. But yeah, all right, so we're over, but thanks very much everyone.
Thank you.